rely on a cross-platform IDE for C and C++. Download now.
All right, folks. Thanks for showing up in the last day. I know it's hard, low energy and everything, and we had the party last night. So I'm sort of on the low energy spectrum myself now. So I get it, last day stuff. But we have an awesome program ahead. If you look in the schedule, there's going to be some awesome sessions today. So look forward to that. And I don't know, gallons of caffeine and tea, I guess. Anyway, let's get started. So, yeah, there you go. Okay, so you saw the title. Probably if you walked in, you're sort of interested in the topic. I want to sort of gauge the room as in what people expect when they see that title, and sort of where your mind goes first, as in who thinks it's sort of first thing that comes to mind is sort of CFFI. That's right. Who thinks about glue code or code generators in any fashion, that kind of deal, right? Okay, I kind of expected. Who thinks about some sort of fat compiler that can deal with multiple languages, or like some way the compiler can understand both languages and do something about it? Okay, fewer hands. Who thinks about linkers? Oh, I didn't expect that. Okay. Who thinks about ABI? Okay. Okay, looks like you're in the right room. All right. So usually when you ask people about Rust and Interop in Rust, they would usually think about sort of these known solutions out there, crates doing various sorts of code generation and glue that helps with the story, and they're all sort of good for certain of their workloads and really bad at other things. Sort of, it's not one does everything great story. So I think most of you would be sort of at least heard of them, if not used at least one of these in the past. So there's sort of these are the typical go-to solutions for such things. And of course, you always sort of think about, okay, how am I going to deal with the boilerplate I need? Will I need any kind of source level annotations on either side of the language? Do I need to deal with some sort of abstraction mechanism like interface definition languages? Or how would I map more complex language structures from one language to another? As in, if there's not a good match, it's sort of easy for primitive things, but there's traps even there. Okay, we can deal with strings, but okay, there's traps even there. But if you go to sort of any other more fancy language constructs, either from Rust side or C++ side, it's very difficult to find the right mapping on the opposite side of the fence. And there are sort of solutions that try to do this. For example, CXX is one of these bidirectional things, and they tend to be sort of opinionated, as in they make a call because they can't just like have every possible thing there, and they cover the surface of the language that they can cover, and they make an opinionated call, as in I'm going to map this concept to this other concept on the other side, and if you don't like it, sorry, deal with it, right? So just as disclaimer, I know it's an AI conference, but I'm not gonna dazzle you with any kind of boilerplate generators, and I'm not gonna show you code that you can easily spit out of any code assistant or even Google. So I think that would be sort of waste of your time, because you can do that on your own. I'm going to try to focus on higher level concerns here. Sort of think about the higher level concerns stem from the extreme range of operation for Rust as opposed to other programming languages, maybe. And again, when you look at all these diverse projects and their requirements, both in terms of operation, but specifically in terms of interop, when you sort of have either leaf dependency that you need to sort of write in Rust, or the whole project in Rust, but you have a sort of a dependency in C++ and so on. And depending on nature of the project and how it builds, how what's the operation mode, how it links, um, how dependencies interact in the application. If it's a sort of monolithical thing or it's sort of a dynamic thing that loads stuff, it changes the expectations and what you need and want from the interop story. So frequently when I talk to someone and I ask about, okay, how they think about interop and sort of what are your pain points, they will be very sort of narrowly focused on the area of concerns of their current project or their current need, right? They see sort of what's in front of them, the pain point, and it's sort of natural, right? But if you're trying to figure out how to solve this across the board and identify solutions that would work for most people, again, it's unlikely that you'll find solutions that will work for everyone. But when you're pursuing trying to find solutions that work for most people, then you actually have to do the work to see what are these diverse needs and figure out how they expected them to be used and what are the constraints in each scenario, right? So yesterday in my other session, I talked about sort of the various projects we have going on and even more that are in progress, and we will talk about them later. We see a wide variety of needs in terms of interop specifically, and challenges, and in building developer tools for this, we need to figure out what each project needs and how we can address that specific problem. And again, we're going through a process of delivering this and learning as we do it, right? We can't just spend years in researching the stuff, abstract things, and then we have the magical solution. No, you have to do it. You have to feel the pain and learn from it and sort of develop the tools as you go, right? So we gain experience with this transition. We evaluate the cost of learning, the cost of porting, the cost of writing new components. We evaluate engineering system readiness for these things. We evaluate how much we can automate out of these things. Dealing with debugging hybrid binaries. Yeah, think about having a hybrid binary with mixed C++ and Rust stacked frames and types, and being able to reason about them when you step through the debugger, either with live interactive debugging or when you're doing sort of crash dump analysis, right? So all sorts of challenges. Then there's performance targets. What are the performance expectations of various projects when it comes to these hybrid binaries? Um, People do expect to have cross-language LTO, right? And if you're not ready for such a thing, then your performance compared to what you had, your baseline sort of before migration, it would be disappointing, right? And you say, oh, Rust is crap. Look, my performance after I migrated this component. But you lost a lot of these benefits that were automatically there when you had a single toolchain, single language solution, right? So again, depending on who you talk to, any of these things might be popping up higher on the radar, right? And then sort of costs of maintaining these hybrid solutions, because just doing them and making them work is just sort of half of the story. Just maintaining them and evolving them over time and sort of modifying where the boundary is, because components start out small and then they grow over time, and sort of the surface area of your interop changes over time. So again, I said earlier yesterday, C++ is not going anywhere. There's gazillion lines of C++ code out there and more written every day, right? So in order for this relationship to be successful, we need to sort of play nice with each other. And Rust needs to meet C++ where it is, because it's more likely that C++ is more uh, rigid in adapting to these needs. That doesn't mean it won't happen. So having seamless interop between C++ and Rust components is essential for the success of the symbiosis. And of course, there are many, many challenges. It's not an easy thing. And there are solutions that I showed a bunch of them in earlier slides that just maybe work for certain scenarios. But dealing with API compatibility and platform-specific needs and toolchain guarantees for each platform are sometimes not satisfactory. Also, dealing with CFFI can be difficult, if not disappointing, many times, right? The need to lower at that level. So there's various technologies and glue code and ways to deal with this. But they either tend to be not ergonomic or sacrifice performance in some cases, or they tend to be tied to a specific compiler toolchain. So again, mono compiler culture and assuming things that are in a single universe, on a single niche, might work for many projects or for many companies that are sort of in this, oh, I'm only dealing with LLVM, so it's gonna be easy for me because I'm only in LLVM world. So I have my Rust in LLVM world, I have my C++ in LLVM world, and it's gonna be easy for me, right? What happens if your C++ is in GCC? What happens if your C++ is in MSVC and so on, right? So again, there's considerations related to more than just the thing that's in front of you, the source code that you need to interact with. So I aim to sort of evaluate some of these concerns, show some of these challenges, see what we can learn from, and tell you what are sort of active areas of development for this. So in terms of interoperability, there's sort of some high level goals based on, let's say, union of discussions with various teams and projects and their needs. Nobody likes to use unsafe excessively just to be able to talk to C++, right? Nobody wants perf overhead. Even projects that claim that they're not perf sensitive, they just don't want to hear about like, oh, I'm going to pay for this thing. Nobody likes boilerplate, right? Even if it's automatically generated, it can be a pain to maintain. Like having this stuff hang in your code base is a pain. So manual annotations are difficult. Nobody likes to do that. Auto generators, yes, they can do the job for you, but you have to check that thing in or sort of deal with it as in it's in your face every day after that. And think about if you have a very wide API surface. Let's say you have, I don't know, have a service that has 10,000 APIs or something like that. Like, do you really want to have 10,000, those 10,000 definitions replicated in both languages so you can deal with them on other side? So boilerplate is not something that's desirable in many situations. I hinted about this earlier, the broad type support and with safety, right? How do you map concepts and not have to lower everything to bytes and sort of primitive things? Avoid lowering to CFFI. The ergonomics, right? Can it be sort of easy to do, or is it just a pain and then people just avoid crossing this interop boundary and try to keep it like as tight as possible? Working with dynamic libraries, many people just tend to blissfully forget about this, right? But there are many projects out there that need to deal with dynamic libraries and all the weirdness that comes out of that, and they expect Interop to play into this scenario as well, right? And of course, the C++ API considerations, and talked about automation earlier. Build systems. I'm not going to talk about this today, but build systems and engineering systems and how these come into play with hybrid projects is crucial, again, for developer toil and sort of the friction that these things can cause. So again, you can make it work, but probably it won't be pretty. Monorepo-like scenarios and sort of unified build systems can help, but not everyone is in that sort of camp where they can afford to do such things. So I'm going to make a big claim today. And the claim is that although the interop libraries are important to the story, I'm going to make a claim that more important to the story is what we do in the compiler and linker and the API guarantees specifically for this interaction. So I'm going to focus on this presentation, sort of the episode 1 on the ABI story, right? Okay, this is sort of the mandatory intro slides and places where you can yell at me if you don't agree. And the disclaimer, just this is sort of my opinion. Like, I'm not representing here my employer. And yes, I've been fighting these demons for a while, so I'm still working on it. So bear with me. Let me start with sort of a cautionary tale, right? Because I'm going to focus the rest of the discussion on sort of the binary aspects and sort of the code generation, sort of thinking about the back end of the compiler and how to deal with this at binary level. Let me start with sort of a cautionary tale in ABI, right? I'm sort of at a predominantly C++ conference here, so I don't think this is sort of any news for you. But it's sort of something that happened right before the pandemic in the Prague ISO C++ committee meeting, where sort of the last time this was discussed. And sort of the discussion was whether or not to acknowledge C++ has an ABI to break or not. So it sort of was a rather unsatisfactory vote there, and many people were not happy with the outcome. I do recommend to read this article if you're sort of interested in an amusement take on the story. But no, this is not going to be a sort of an ABI now or never kind of presentation. I'm not going to try to convince you of how this thing would should be handled in C++. But I want to sort of analyze if ABI resilience should be part of the language design and how tools should be able to operate, or is just a sort of implementation side effect that we can just blissfully ignore. So I'm going to talk about ABI stability, sort of benefits and risks it brings. I'm going to cover dynamic linking, of course, in the context of Rust C++ Interop, what it means to design for ABI resilience, how ABI resilience can play a role in library evolution, and sort of performance implications. And I'm going to sort of try to pick some things that we can learn from other places, other languages. I'm going to give some examples. And talk about ongoing efforts in the Rust community around this, and sort of where we are, and sort of short-term solutions versus long-term goals. So ABI can mean a lot of things to different people, right? It's platform, hardware, calling conventions, compilers, standard library. Like, people tend to think of this as just implementation details, something that my compiler needs to deal with. It's not sort of a concern for user level. So ABI stability isn't technically a property of the programming language. It's more of a property of the system and the toolchain. And it's definitely influenced by the platform that you're targeting, right? And the platform owner can require specific compiler toolchains and what it means in what it expects in terms of ABI. And of course, if you care about dynamic linking, like I mentioned earlier, and shared libraries, then you definitely care about ABI. So roughly, these are sort of top areas of concerns for ABI in terms of layout of types, size, alignment, stride in some languages, offsets of fields, vtable entries, closures, calling conventions, name mangling. This is a big one. People don't usually think about name mangling, but it actually makes a difference when you want to debug these hybrid binaries. And where applicable, metadata. So why should we care about ABI stability? And I think this is fundamental. And I notice people tend to sort of be defensive about some of these things, as in, so, oh, they're not that important or they're not relevant, right? They might not be relevant for your project, but they are relevant for other people, right? For example, not everyone wants to share the source code of their library. I know, shocker. And a library author might want to use the most recent version of a compiler without the fear of sort of limiting the audience of their libraries. You want libraries to be compiled with different compiler versions and sort of be able to mix them up and still work. You want to avoid recompiling everything all the time. Yes, there are projects that sort of take the route of compile everything from source, compile everything all the time, right? I'm going to ignore caching, but uh, not everyone can afford to do that. Some projects are really big, or some dependencies are not in your direct control, and you still need to be able to use them. And you want to be able to ship and update independently your binaries. Think about applying patches, right? This is crucial for some workloads and some projects. Being able to update binaries independently or patch them, sometimes even hot patch them, is essential, right? So being able to reason about layout in these scenarios is very important. And of course, multiple programs can share the same library. Like think about even the standard library. Then there's plugins, extensions that are dynamically loaded. Think about what applications need to deal with it to be able to load plugins, right? And of course, the elephant in the room, language interop. And I often hear this discussion, even when I gave a previous version of the presentation, as the discussion was, yeah, this all sound good, but I'm not sure when I would be able to commit to freezing the the layout defined by my library. I was actually talking to a library author, uh, was sitting right there in front of me, and he was like, yeah, sounds good. I want that, but I'm not sure when's the right time. As in, I might regret committing to something, right? And I agree. Yeah, it's never the right time. It's like you can always think of, oh, I might discover something a month from now, and then I regret sort of committing to something, committing to a specific layout. And even if we look at our dear standard library, we can see such bad decisions, right? Uh, so you don't want to shut the door for future compiler and library improvements, right? If you're stabilizing too early, you miss optimization opportunities and improvements, right? Um, if you're delaying it indefinitely, like people tend to do in Rust, then you're never going to have a solid story that will serve everyone, right? You will say, oh, we want to keep the door open because we're sort of in flex 10 years later. But anyway, uh, that means you're just shutting the door out for many use cases and many projects. And mind you, these are not impossible things. They're tough things. They're tough to solve, but they can be done. And I'm going to show some examples. So it's just a matter of awareness and people being willing to fund such efforts. So when we talk about stability, we also talk about sort of evolving software libraries. Because if you're building something monolith, there just you control every part of it, then you care less about this stuff. You should, but maybe you're not that pressed. But if you're building and evolving libraries that others consume, then it really matters. Um, so developers want to be able to evolve their library without breaking ABI, right? Add functionality, fix bugs, improve performance, and so on. And many things that you might want to do that you will just break this contract if someone expects it. So let's maybe look at a quick scorecard here. That's what we can learn by looking at others, right? So we kind of see this situation is rather disappointing across the board. Um, C++ doesn't acknowledge a position here, but we all know where it is. Um, and the only one that sort of has something different there is Swift. And that's because Apple cares about shared libraries and about servicing and about size and about patching them and so on. You don't want every app that you install on your phone to come with a gazillion frameworks linked statically into it, right? So Rust has never had a stable ABI. Um, there's an asterisk there, but I'm gonna make fun of it later. And it was not designed with a stable API as a primary goal. This is still an unsolved problem 10 years after 1.0. And some people refuse to acknowledge that this is an important problem. And I think that's why we're not making significant progress. But there is movement. More about that towards the end of the talk. Zig natively supports CABIs for external things. But again, C has a much tighter love story with C, so it's sort of expected there. Go has a concept of ABI internal specification, but it's not something that it offers sort of at user level as at Go level, right? So it's sort of a more wishy-washy story. Still, they don't want to commit to actually specifying an ABI. Carbon outright claims that this is a non-goal and sort of we're too early. Check on us 10 years later. And of course, the greatest champion of ABI stability is and dynamic link is C. This is C, not Carbon, by the way. So many software ecosystems require both long-term ABI stability and the ability to evolve, right? Because you can't just say, I'm done with this library, right? So many of these systems, because C tends to be sort of this common denominator lingua franca of all the compact things, they tend to use this as sort of their conformance layer of their sort of interaction with the outside world. But software components, evolving these software components through CABI requires manual and proactive usage, as in levels of indirection, narrowing, lowering your things, duplicating things so that they're representable through this narrow view of the world. So again, if your API surface is small enough or you don't need any fancy vocabulary things at the surface, it can be very, very well suited for your project. So there's no need to sort of go for big guns if your problems are simple. Like, I'm not encouraging here to use the most expensive, most fancy machinery if you have like 2 functions that you need to call into some DLL. What's the point? We all love this one, right? This solves all your ABI requirements. Well, and if we look at especially in Microsoft, if we look at all this story, we've been dealing with this crap for 35 years, right? If you go back to COM, which is very much at the core of everything that we're doing even today, it's the ultimate interop story. It's the ultimate ABI story, right? But it's maybe not the most loved technology out there. I like it, but it's sort of, I know I'm in the minority here. Again, it has the idea of interface definition language to describe these things, and it handles sort of evolution by sort of projecting various things in terms of interfaces. I think we've all seen stuff like that. And then there's the sort of at the, in my opinion, sort of at the other end of the spectrum, sort of the complete mess of sort of opaque things, a la Objective-C message send, or sort of unstructured data, as in sizzle everything and just I'm going to intercept the message and I'll figure out what to do with it. Any people still remember Objective-C? 3 guys in the back. Okay, so clearly people have opinions about this stuff. Anyway, these are just for your amusement. They're not essential to the story. So C++ is sort of the king of mixed signals and ambivalent behavior when it comes to this sort of stability story. C++ does not have an ABI resilience model. C++ committee will just reject any proposal that, take into consideration any proposal that will cause ABI breaks. And implementers, which I work for one, will just not change, improve library components because it will cause ABI breaks. So you have lots of crap implementations out there just because you love your users and you want to keep them trapped around. So C++ will not officially commit to guaranteeing ABI stability, but in reality, it's frozen as bad as it is, right? So um, yeah, WG21 is not in favor of an ABI break anytime soon, but it could happen sometime in the future. I don't know. I'll be wrong, retired. And they will take their sweet time to analyze any proposals that will be against this thing. Okay, so sort of, it's a tough place to be. I get it. I get it. And we've made some of these missteps in the past, and it took many years to get over them, right? People do remember the string story in GCC, right? Okay, that took more than 10 years to get over, right? So I think they still have the flag to choose between the two implementations. Yeah. Well, yeah. So why do we want to break ABIs? So we want to fix stuff, right? If we're just in the context of C++, there's so many broken things in implementations. And I'm not just talking about one crappy one that you all love. So there's opportunities for better conformance, more efficient implementations, tweaks, and sort of things that can be done better. Just I'm listing just a couple of them. They're by no means an exhaustive list, right? By the way, if you're not aware of these things, like get familiar. And there are some escape hatches there. There's, for example, libc++ has some ways where you can tap into sort of experimental stuff. My experience, people don't know about these things. I'm not even sure if you should know about them. Kind of feel guilty that I'm sharing this, but anyway, I'll move fast. So I think we need to sort of start looking at alternatives, as in what we can learn from others, both for C++ and but specifically for Rust. I'm more concerned with Rust these days. So there are differences, and I want to acknowledge this. The communities, the intended audience, the sort of applicability of these languages and frameworks are slightly different. Sure, they claim common ground and they say systems programming and whatever, but they're not sort of all on the same step of systems programming. So the constraints will vary slightly. So I want to acknowledge this. So I'm going to, because out of my previous scorecard, Swift had the only sort of ABI resilience story out there. I'm just gonna pick on that a bit and see what we can learn. And then I'm gonna move on to Rust. And show you that it's actually a good place to learn from. So if you're not familiar with Swift, how many people are vaguely familiar with Swift? Okay, I see a few hands. So that's sort of the Swift 101, as in sort of what should expect from such a language. This language was designed for library evolution, right? And was specifically designed to account for stable ABI. It didn't have it from the start. The Swift ABI resilience model came only in version 5, so many years after the first version. But it was always sort of designed with that in mind. And the fact that the story came later and how they designed it in for the future will also show that it's never too late, as in the fact that you didn't design it from the start doesn't prohibit you to sort of think about this. So principles of stable ABI evolution is make all promises explicit for users. Delineate what can and cannot change in a stable ABI, right? Provide a performance model that indirects only when necessary, right? To avoid any sort of hidden costs for this resilience model. And let authors of libraries and their consumers control this mechanism. If you want to sort of see a lengthy presentation about this, I highly recommend this one by Doug Greger. By the way, my slides are full of links. I'm going to share them later. So if you care about any of these topics, you can just investigate on your own. So let's look at the simple struct. And again, you don't need to sort of be familiar with Swift syntax. Just your typical things where you see question mark, that just means it's an optional thing. So persons person struct changes size when new fields are added, right? Offsets of fields change whenever layout changes, right? So you can see in this example that we operated some changes on this structure, right? We added some fields, right? Stuff moved around, right? By the way, where you see the bracket syntax, that just means it's an array. And you can see that in the getter function there, we access an offset into the structure. So all these operations are susceptible to layout changes in the structure, because now we're using a different classroom structure that has these person objects inside. So any change in person will percolate into this other structure, and it will affect how it can reach out and see into these nested objects, right? Including offsets. But you also see an array there, so stride matters as well. Swift has a concept of stride. So type layout should be as if we had the whole program, right? Person library should lay out the type without any indirection. Right? Again, you don't want to pay any cost when not necessary. And in order to do this, you need to rely on some form of external help, some form of metadata. And Swift chooses the sort of the route of metadata. So you need to expose layout information in terms of size, alignment of types, offset of each of your public fields, and so on. So the compiler will actually play a role in this, and it will generate all the required metadata so that when it sees and links these things together, it knows how to do this the right operations to adjust any kinds of layout changes. Client code, external code, always indirects through the layout metadata. So for accessing a field, it has to read the metadata for each field offset, add that offset to the base object, cast a new pointer to load the field, and so on. Storing an instance of the stack, again, you need to read metadata to figure out the instance size, right? And emit the right alloc instruction to set up the stack as needed, right? Again, you need compiler functionality to play a role in this. Library code, that's the internal code, right, eliminates all indirection, because the library code already knows its layout. It's a sort of an autonomous thing, right? So when it reads and accesses a field, it doesn't need to go through the metadata because it is compiled as a whole there. So it just adds the offset and custom new pointer, sort of eliminates any indirection that is needed by external code. So that's sort of first difference right there, as in you have the information exposed through metadata, and you treat things differently in the compiler based on if it's internal code or external code, right? So you need compiler support for this, and LVM support for dynamically sized things on the stack has been very good for Swift, right? And Swift makes heavy use of this for ABI stable value types. So you don't need to know the size of the thing until load time. And by the way, these things are also optimized to not be done every time on every access. If you think, oh, all this metadata computation and loading the metadata happens every time I'm accessing things, it sounds like a very heavy runtime and it should be super expensive. No, they do this thing when you load in a library, right? So at load time, they do this metadata ingestion, and then it just a pure arithmetic, just doing some additions, right? So this information is done once, sort of ideally per process lifecycle, and it's cached, right? So it has minimum runtime impact. And when it's inside the resilience boundary, and I'm going to talk later about resilience boundaries, you don't even pay that cost because it bypasses completely this mechanism of indirection. So dynamic allocs can handle this very nicely. But at the sort of opposite end, C++ desperately wants all objects to have constant compile time size. So it's sort of a mismatch in sort of expectations. And the notion of size of an align of being sort of runtime values, just it's sort of not something that C++ can agree with. So again, resilience domains are about explicitly modeling these boundaries between software modules that evolve separately or together. I gave this example earlier with the person and the classroom structures and so on, but you can think about sort of standard library and application code, or I have these two different libraries. Some of them are mine, some of them are systems, some of them are third party, and so on. Again, all these form resilience boundaries, or resilience boundary can be a single library or the application code, or can be two libraries, or can be my application code and one library. So again, you're in control of how you define these things. When things evolve together, you can consider them a single resilience boundary, and because they evolve together, they compile together, you don't need to pay for any of these costs, right? Even if you talk across libraries, across modules, if they're in the same resilience boundary, you don't pay any cost for these sort of modifications because they know about their internal structure and changes. They're always fresh. But when things evolve separately, even if they're yours, or if you're talking about system libraries or third-party libraries, then you consider that sort of foreign code, and then you have to sort of provide these indirections. So in this example that I had earlier, right, we have three resilience boundaries. We have the operating system and sort of system libraries, the person library, classroom app, and so on. So whatever is compiled together is in the same resilience domain. So optimization. So across resilience domains, you want to maintain stable ABI within a single resilience domain. So within a sort of green bubble there, within a resilience domain, all implementation details are fair game, as if said, you can break everything, like in the good sense, right? As in no indirections, no guarantees. You just assume all the parts within this bubble, see all the changes, and they're compiled from source and evolve together. So again, optimizations need to be aware of these resilience domains boundaries. So what if we have only one resilience domain? As in we say, okay, I control everything. I don't want to deal with this thing. It's sort of an overhead for me. I don't want to think about it. I don't care about it. I don't want to pay for it. Sure, you can have a single resilience domain, and then it's just as if you don't have any ABI resilience whatsoever, right? There are no ABI stable boundaries. All layouts are fixed at compile time. ABI stability is completely irrelevant. You don't pay for anything, right? So you can play that game and say, I don't care. So again, this is about you being in control of how these play out. So there are sort of some defaults that I think they're sane that Swift puts out. So by default, a type that is defined in a dynamic library has resilient layout. That's sort of the default assumption. You can change it, but that's the default assumption. Size, alignment, stride of that type aren't statically known to the application. So you must ask the dynamic library's type value witness table at runtime. This is the thing that I mentioned earlier, where it's sort of asked when it's loaded and cached. It's called the value witness table, the metadata. So it's just the table of stuff you might want to know about type and ABI. I won't go into details. I have a few links to articles if you care about mechanics of how these things can be implemented. It's not that complicated. And it's also not tied to Swift itself. It's generic concepts that can be applied to any programming language that lets you control memory layout. So this results in resilient types having to be boxed or passed around as a pointer. It's not quite true, but that's sort of the as if feeling. Okay, the details are interesting there. That's a link, by the way. Uh, and inside the boundaries of a dynamic library, where all its implementation details are statically known, the type is handled as if it's not resilient. So no indirections whatsoever, right? So this is the default behavior. So Swift ABI resilience is the default for libraries. And you have opt-outs if you don't want to do it. Again, you're in control. And you can trade future evolution for client performance. For example, explicit inline code exposed into the client enables color optimization, generic specializations, prevents any changes to functional semantics, right? This is one example, right? Those at things are just sort of attributes in Swift. They tell the compiler stuff. So fixed layout is another such attribute, right? Fixed layout type promises that the type layout will never change, right? I'm defining a pair, god damn it. How many things can be changed in a pair, right? Well, yeah. Anyway, you have that, right? So when you explicitly think, okay, I'm done with this shit, right? I'll never change it. And it's sort of a fundamental thing. I don't want to pay for any kind of extra math to find offsets into this thing, right? There's your escape hatch. You have an attribute for that, right? So it has a large runtime component, but by large I don't mean it's necessarily an expensive thing, but it's sort of a larger than Rust, larger than C++ kind of thing, right? But it does many other things. So this runtime doesn't handle just ABI resilience, of course. So um, it does all this business with complicity from the compiler and LLVM. Handling the metadata, these witness tables and indirections, handling generics and monomorphization and reabstractions. These are sort of tougher things. And I think Swift does a remarkable job, even in the context of generics, which is, if you think about it, it's kind of mind-bending. That's one of the articles that I recommend you reading if you're curious about how these things can be implemented. All right. So, no question.
Swift does this just
There's a mic coming.
Swift only does this for compatibility between different Swift components, right? They don't do this for interop with other languages, or do they?
Yeah, that's the purpose, the motivation. But that being said, in the Swift community, there's an active effort right now. Let me repeat the question. Sorry. So the question was, Swift does this resilience story for ABI for its purpose of evolving its libraries independent and shipping them and patching them and so on, not necessarily for interop with other languages. That was sort of the observation from Andreas. That is sort of the primary goal for them. That was the motivation to do the work. But right now, there's an active effort to do Swift C++ interop, and they're sort of very much invested behind making that work. And that will be a combination of properly handling ABI stability and the fat compiler strategy that I alluded to in the first slides, where they will make their Swift compiler be able to compile C++ code as well. So it's it's going to be an all-in-one compiler. It's sort of Swift compiler will have a Clang built in. It's a rough way of saying things, but that's the right mental model, I think. So it will play a role, but it wasn't the design of intention. I've seen very active interest from Apple and in general Swift community for making Swift C++ interop work. Very recent. It didn't used to be a sort of a top concern. Anyway, so now going back to Rust, and so like can we have any kind of form of stable API? And I made fun of this earlier, but people tend to think that this is sort of stable API for Rust, and technically it is true. But I'm sorry if you have to do this, it's gonna be painful, right? Again, if your needs for interop are simple enough, this can be not just the right thing. So I'm not trying to sort of downplay it. It's good, but it's sort of such a poor tool for generic things. And in general, Rust FFI itself is sort of zero cost, and it tends to have the same performance characteristics as calling C, C++ code. And so it tends not to be a costly interop boundary. You can run into traps, and people sometimes fall into these things when they don't realize how they map these things over the interop boundary. One example is that I've seen many times is they get burned by string representations, because they will map strings, but then they will pay an invisible cost in sort of reinterpreting the encoding of these strings. So they sort of think that the cost comes from the marshalling itself, but it's sort of a hidden cost because you're interacting with some library or some platform that expects a different way of encoding things. So anyway, so the status quo is fake it till you make it, and Repr C is sort of the go-to for when you need to deal with this in Rust and sort of project a stable layout. So you have things like using C calling convention for function definition and calls, right? Extern C FN. Using C data layout. Definitions of C types like char, int, long, like very basic stuff. And they're sort of accessible in the type system on the Rust side as well. Exporting an item under a stable linking symbol, no mangle. Mentioned earlier, like name mangling is highly important part of the story. People tend to obsess with compilation because we ship those bits, but you sometimes need to debug those bits too. So name mangling is important, and there's significant differences between Rust and C++ there. It's limited to C types mostly, no slices, no basically all the good stuff you would want on the Rust side of things you don't get, right? So you have sort of the poor man's interop story. It works, and again, I'll stress this again: if your needs are limited, why bother with anything fancy? Use the cheap, quick thing, right? But that sort of means you're sort of you need to either lower your vocabulary types at your API surface, or you need to expose as little as possible through that surface. As in, you have your API contract and you expose some shitty thing C so that you can talk to other components, and you lose any kind of expressiveness or safety over that boundary. It's sort of, trust me, I'm sending you some bits here, deal. So yeah, so what you want is a stable calling convention that supports common data types. Like think of the Krabby experiment. This is sort of started a few years back, and it's still in flux, I would say. But it's an experiment that we can learn from. Some people actually use it for real stuff, right? If you're not familiar, I put a link there so you can look at it. So you want slices, right? You want a standard data layout that supports enums with data payloads, right? Again, Repr Krabby helps with that. Stable layout guarantees for common standard library types. Think about the Rust standard library is littered with option and result types, and all your APIs hopefully are written in that fashion too, right? They're using sort of idiomatic things. Right? How do you map this on the other side? And what's sort of the guarantees that you offer on the other side? Yes, you have helpers that will do this mapping for you, for example, CXX, right? But what are these sort of stability guarantees of that representation on the other side? Again, you want maybe even further mechanisms for exporting and importing naming symbols, working with dynamic libraries I mentioned earlier. Not everyone can compile everything in a monolithic binary, right? Dealing with dynamic libraries is very much a thing of concern. How do you export items under stable linking symbols, supporting crates, modules, methods, all the fancy things from the Rust ecosystem? How to deal with that? And what role should the compiler and linker play in dealing with this, right? And how would it look on the source code side, and what should the compiler and linker do? You want to use a crate as a dynamic library or importing the exported items out of there, right? Something like, again, this is sort of science fiction syntax. Don't try to put that in your code. The crabby things will work. I consider it sort of prototype level, but this stuff is sort of like really out there. But it's something that people want, right? We just need to make some steps in that direction and create tooling for this. So use a crate as a dynamic library, importing only what you need from it. Cargo features for dynamically linking for Rust libraries. Again, cargo plays a big role here, not when you think about just Rust compiler is just one side of the story, but sort of orchestrating builds and dependencies and linking, and sort of you need compiler features and cargo features. So it's sort of an interplay to make things happen. If you think even further, like even fancier things, trait objects, vtables, and type ID things, right? Standard layout for dynamic trait objects. These are a thing in Rust. People use them. Sure, they're not sort of everywhere, but you need to interact with these things. A way of dealing with types that depend on global states, like allocated objects, right? Basic representations of box types or vector, stuff like that. Type ID, how to deal with erasure things like any. This also sort of involves how to deal with catch and wind and panics and exception handling. Also, people think that exception handling in Rust is not a thing. It's not a thing in sort of for control flow, but it happens behind the scenes. Like when a panic occurs, you do have unwinding. Right? The compiler knows to do exception handling and do unwinding. It's a complicated process. And you need to think about how this interacts in the context of interop, as in what happens when I have mixed C++ and Rust code and an exception occurs. Either a panic on the Rust side or an exception on the C++ side. How to deal with that, right? What happens? What happens with unwinding? Then there's access to standard data structures like maps through dynamic standard trait objects. Again, people just, when you put your mindset in the frame of I will deal with this in C way, right? Then you don't think about all these things, right? You just automatically sacrifice all the expressiveness and all the stuff that you had in your API in order to communicate through a very lossy medium, which is the CFFI. So you tend to forget about all the nice expressive things on the Rust side. So even beyond that, turning parts of the standard library into opt-in dynamic library with a stable ABI. For example, standard library as a dynamic library rather than statically linking it in. And more important than that, tools to help detect and maintain ABI compatibility and tools to debug ABI issues. This is an area that I care about a lot. I'm in the tools business, right? So I care a lot about sort of how can we build such tools. And I gave you one example there, ABI Cafe, and a very good article that's sort of related to this, by the way. I highly recommend reading that. It's on the lengthy side, but it's good. So just having it work right now is just one part of the story. How do you ensure you don't break your interop by slightly changing something on either side of the thing. So you need proper tooling to detect these things and warn you about them, and even to debug such issues, as in figure out, okay, I figured out there's a problem with the ABI in my interop. Okay, but how do I figure out where the problem is, right? Because sometimes can feel like a needle in the haystack thing. And even, why not, even the ability to do introspection, right? Based on these things. So these are all sort of very interesting concerns. And people are like me and others are thinking about this, but they're sort of a bit farther into the future. And I made this sort of this whole story with Swift and talking about this stuff, and sort of probably many people think it's like, what does this have to do with Rust? As in, it will never work for Rust. Well, there are people who are actively looking and learning from the Swift story, and they're I highly recommend this one. I didn't know about this. I found out about this fairly recent, at the beginning of this year. It's from last year. It has sort of a similar title, something like ABI, the path to stable ABI for Rust. Yeah. So it's sort of using the Rust types, the right trait system, and trying to emulate the Swift way of ABI resilience for Rust. It's sort of an interesting experiment, and even beyond the experiment itself, I think it's sort of very valuable, sort of the first half of the presentation, again, as a sort of reinforcement of why this is crucial for Rust, and sort of what are the problems that this is trying to solve, sort of reinforcing what I said too. But you can hear it from someone else if you don't believe me. By the way, this is the author of the hash brown library, so I think you can trust him. So I highly recommend looking at that if you're interested. I was so ashamed that I found about it so late, but very good. Anyway, for this shiny future for ABI in Rust, I think the consensus is, at least for the people that are interested in improving the status quo, is that it's unlikely that we're gonna be able to commit to some solution that will just be okay for everyone, ignoring REPR-C, of course. So it's probably gonna end up being either sort of a resilience story, hopefully, or a wave to represent and commit to multiple ABIs for Rust. So it feels more like the likely scenario, because it feels like it's cheaper. But ideally, I would want something like this, but this is sort of not easy. So some of the active effort in this area. So the Rust Foundation has been specifically funded and received grants with the specific intent of improving the interop story. And not just with C++ in general, but you can imagine C++ is sort of the top concern. So they are specifically funded for this charter. And this year, to my pleasant surprise, is I've seen a lot of sort of activity in the community around this topic, not just driven from the foundation side, but sort of people start to care about this. And I think it's just a matter of enough projects in industry out there now use significant amount of Rust, and it's becoming a pain point. I mentioned this earlier in my talk earlier about teams feeling this pain, right? When you're doing some tiny little things, some greenfield, some experiments here and there, and just like, I can wing it. When you're starting to put real commitments and have significant traction of Rust in your projects, in your companies, then this becomes more important. And then I see sort of, I think we reached an inflection point in the community where sort of this thing is no return, as in we care about it and people want to make some progress. So this is also officially stated as the one of the project goals for 2025 H1. It's I linked I linked there the articles. Evaluate approaches for seamless interop between C++ and Rust. Tyler Mandry is the point of contact for the project goal if you're interested or you know him or want to reach out. There's the tracking issue and sort of all the details are linked in these things if you want to sort of get involved or learn more. An interesting sort of development is that the Rust Foundation actually joined INSITS in order to participate in the C++ ISO standards process. And John Bauman, who's the engineer that's paid by the Rust Foundation specifically to work on Interop, he attended his first WG21 meeting in Austria, and he outlined some of these goals and the tentative interop strategy from the Rust side, and talked to C++ people, right? So there's steps in the right direction. Short term, the idea is to contribute engineering time to some of the key interop crates. I mentioned in the very first slide some of them, right? As in improve the status quo, as in what people are using and sort of move the needle, right? Because there's always more work to be done there. And while doing this, sort of gain perspective on the sort of challenges and needed solutions that are sort of beyond the scope of these crates, as in move the needle, talk to people, find out about the pain points, see how they're used in real projects, see how they're used in industry and so on. And there's an active outreach, not just in open source, as in active outreach where they want to talk to companies to figure out what they're doing, because they can only see what's out there as in public projects, but they want to learn from companies. So if your company or your project cares about these topics, do reach out to them, talk to them. They want to hear your challenges, your constraints, right? And they don't have visibility into this, right? So long term, you want to evaluate sort of approaches for seamless interop. They're working on documenting the problem space and the current challenges. Again, make sure that your needs are sort of captured there, because nobody will try to make progress on improving the status quo if they don't, for your particular view, if they don't know about it. So sort of that's sort of the strategy for Interop through the foundation's perspective. We had a first meeting about this in February. It was a lengthy thing. The notes are very valuable. So at the very least you can do is go through the notes from the first meeting in February. I'll link them there. You can probably also Google for them. There they do an exposition of the challenges of the status quo, some of the existing workarounds and solutions, some of the aspirational stuff, like things I mentioned myself. Definitely valuable. At least read this thing, as in even if you're not planning to actively attend these things or sort of drive them, at least read to know where it's going. So that's sort of was from February. If you do want to sort of actively participate, or at least eavesdrop on, on the thing, do connect to the Zulip server for Rustlang. There is a specific interop channel. It's not super high noise, so don't worry that I'm going to be swamped with people talking about stuff. So it's sort of lower traffic, it's manageable. So you'll even find lots of C++ people there that are becoming very interested in this topic. So I'm pretty sure you'll recognize some names there. And if you care about the next meeting, the next one is going to be on April 23rd. It usually happens over Jitsi. If you want to just listen in, or if you have something to say, do come. Everyone is sort of invited if they care about this and they can bring something valuable to the table. Also, very good read is Nico's recent post on Interop, sort of meant as a way to It's more of on the aspirational side and meant to sort of rally the community behind these goals. It has very good information too, so you might have a read of that. It's not lengthy. So if you care about this, I'll see you there, I guess. So I would say I'm sort of almost done with my rant. I have more to say, but I'm actually more interested in what you have to say about this. So um, we also have time right now, but if you feel like you're not comfortable in sort of sharing stuff sort of on camera, I'm more than happy to talk about this sort of one-on-one or in smaller groups in the hallways or over lunch or something. I really care to learn more about sort of what are your requirements in your projects, on sort of what are your expectations and constraints with regards to Interop in general. So I'm super curious because, like I told you, I'm in the business of building tools for these things, and I want to talk to as many developers as possible to make sure I understand the whole picture, and I want to learn from you.